I don't know about you guys, but I find that epic. Hey guys, Lucas here and welcome on K's New Space. Today another coding tutorial in KSP using Python and kRPC. 2 episodes ago we developed a flight computer which can make a rocket hover. For that we plug in a desired altitude and the computer will decide a speed. In essence, the closer we get to the desired altitude, the lower the speed becomes. Let's try it with this one. And launch. As you can see, it works. But the problem is, especially on bigger rockets, it starts to wobble like crazy. So it's not an ideal solution. The goal of this video is to change that and to introduce a smooth throttle. Let's go! Now back with small ship and our boilerplate code. However, I did a couple more changes, so let me first introduce those. I decided to put all the code required to connect to KSP into its own function. That function I put in our k.py file, which I import here. Let me check it. First I import the kRPC module, then I connect to KSP. I assign variables to the 3 main objects we need, which is vessel, controller and telemetry, and I return them in the function. Over here I catch them using the same variable names. And lastly, I also changed how I handle key input delays in order to avoid detecting key presses multiple times by holding the button too long. For that I use these functions here. What these do are they define a delay, and that delay gets raised to 5 every time I press a button. And this update function here runs every time the loop iterates to decrease the delay again. So in essence, it takes 5 loops until I can press each button again. I don't use this for the escape button though, because that just ends the program, so it doesn't matter. Starting from scratch, I want to do things a little different this time. Instead of focusing on the altitude, I just want to handle the speed. So instead of desired altitude, I will use desired speed, which I initialize like so. And of course, what we need for this speed are 2 altitude values, one from the loop before and the recent one. So again, like we did, I think in the last video, I will define last altitude over here. And of course I also have to initialize it. And using telemetry I can define the values here. So current altitude equals telemetry dot surface altitude. And the speed becomes last altitude minus current altitude divided by dt. Again, just as a repetition, speed is defined by distance divided by time, aka meters per second. So the distance we went up is the last altitude minus the current altitude, and the time it took to move the distance was dt. Okay, let me check again. Yeah, and now I also want to print it on screen using the print function. And let me take 2 decimal places. Okay, that should do it. Now let's test it. Oops, an error. Oh yes, this is just DT. Okay, let me test it again. Yeah, I did some changes before I started the video and I forgot to return them to normal. Okay, again. Always the same mistakes. I forgot to move the cursor. But now. Okay. Here we have the throttle that works. And let's check if it also correctly displays our speed. Let's compare it here. 3 meters per second. 4. Yeah, it's about the same. Of course, the KSP internal speed is a little bit more precise, I think. But that's okay. That was, of course, a manual landing. Let's quit out of this. So what I now want to do is to change the desired speed when I do some button presses. So for that I need a new line here. Else if key pressed. Oh, just by the way, in case you try the same and this does work for you, I of course assigned a new name to this function. So the real function is called keyboard.isPressed. And I imported and changed the name using this keyword as. Just in case that confused someone. Okay, what button to choose? I choose plus this time because, well, my Soyuz rocket actually uses action groups, so using 1, 2 and 3 is not optimal this time. Okay, so else if key press 0, and of course let's not forget our keys delay is equal to 0. That's of course this delay here. This must be 0 so we can actually go on. And now desired speed is incremented by, let's say, 2 meters per second. And of course keys dot add delay. This should do it, I think. Let's try. Save again. Oh wait, we haven't printed it out on screen yet. Let me change that real quick. Okay, and this time I won't forget to make changes on here. Now, oops, that's of course an underscore. Desired speed. Now I'm pressing the plus. Oh, plus also changes the zoom level, but that's okay. Ah, wait. We forgot to also decrease it using minus. Okay. Now that works. This time is also important that we keep it negative so that we can actually move the rocket down, not just up. Okay, that works. Now I can start developing the flight computer again. Like last time, we will use that to control the throttle. So let's hand over the controller. And we also need the speed. However, I decided instead of handing over all variables I might need one by one, I will simply group them up inside a class called data. This indentation makes sure they're all grouped together. So now instead of calling them one by one, I can simply hand over data like so. And in order to also get my speed, I have to actually define speed in here as well. Speed, or let me say current speed. Like so, and here I think we did that in the last video as well, so that shouldn't be too confusing. Okay. Same for desired speed. I did that. Current speed. What's missing? Okay. Let's test it. Flight computer is missing. Ah, well, we didn't define it yet, so I'll use pass. What does it want? Oh yes, we forgot the keyword define. Okay, I fixed it off screen. I added data dot wherever it was necessary. Now let's start to develop our flight computer. I hope you remember what we did last time. So basically we define a variable ds, which is the difference between the desired speed and the current speed. So data dot minus current. And this difference can of course be positive if the desired speed is larger than the current speed, or negative if it is smaller. So now we're going to use an if statement to differentiate. If ds is bigger or equal than 0, do something. Otherwise, or else, do something else. Like this. And that do something is of course changing the throttle. Controller.throttle. Let's go for a pulsation again, just for testing. So this should lead to the same result we had last time. When the speed is too small, we increase the throttle to 1, and if it is too large, we decrease it to 0.1. Let's test that. Okay. Increasing the throttle. Oh wait, we forgot something again. Or did we? Why doesn't it work? Let me try again. Desired speed is 4. Ah, well, of course. We defined the flight computer, but we don't use it in our main loop. So let's change that. This should do it. Let's test again. Okay. It works, but of course it doesn't respond to our desired speed at all. This shouldn't happen. Let me check again. Oh yes, this pass is of course wrong. My bad. Okay, now it seems to work. Our throttle goes up and down. However, the engine is not activated yet, so let me change that. Oh. I feel like I forgot the data dots somewhere again. Okay, it stops working the moment we go up. Ah, well, why is that speed negative? That is the issue. Current speed. Of course, we switched that around. It should be current altitude minus last altitude. Alternatively, we could add a minus here, but that works as well. Okay, let's test it. The moment of truth. Yep, it works. So this is basically a simplified version of the hover computer without using the altitude. We just control our speed now. And of course, at a desired speed of 0, the rocket hovers. We go up again by 10 meters a second and land by setting it up to -2. Okay, that works. So the idea for a smooth throttle is to not just change it to 1, but increment it by a small amount. Let's say 0.1. And here increment it negatively, or decrement, I think. But of course I don't want to go below 0, so if bigger or equal than, wait, 0.2. I don't want to drop to 0. And here is smaller or equal to 0.09. And of course, don't forget to indent it. So now we are going to add 0.1 if the speed is, if the difference is bigger than 0, so if our desired speed is bigger than the current speed, and throttle down if it's not. Now if that works, that would be quite easy, right? However, I have my doubts. Let's try it. Okay, so now I'm hovering. I mean, we're still hovering and it's kind of smoother, but we're oscillating. So what we now ran into is a very common problem in control theory. We oscillate around a desired value. And you might think, well, maybe we just need smaller increments. So let's just try that one out. Oops, that was too little. Here we go. You can see the throttle goes up much more slowly. But as you can see, the issue is our oscillation gets even bigger. Now why is that? Well, the reason is simply because with lower increments we also increase the reaction speed of our throttle. So as we overshoot the speed, it takes much more time to correct the throttle. So let's do the opposite. Let's pick bigger increments. So let's use O.2. Now this should in theory improve it. And indeed the oscillation got better. And you might of course see where this is going. If we wanted to minimize the oscillation this way, we had to go back to pulsating the engine. The pulsation is the biggest amount of increment we can use. The fastest throttle response, so to speak. Okay, let's land again. By using those maximum increments, I basically cheated myself around having to deal with those oscillations. But now I want to fix that. How? That's the question. Now, of course, I've done a lot of testing in the background, so I already kind of know the answer. I really don't want to bore you with hours of experimentation. So there is an underlying problem we have right now. We try to control the speed using throttle, but the throttle doesn't really control the speed. There is a property in between speed and throttle, and that is acceleration. So the throttle actually controls the acceleration, and the acceleration then changes the speed. But how do we keep track of that? Well, it's quite simple. Acceleration is to speed what speed is to altitude, so we have to do the same, just using speed. Okay, let me add it here. Current acceleration, and of course we will also need last speed, like we used last altitude. Okay, last altitude is here. We will also add last speed. And we will calculate the acceleration over here. And of course, we also have to divide by dt, because acceleration is equal to speed over time. And that of course becomes meters per second squared. Wait, data dot dt of course. Okay guys, again, our current acceleration is the current speed minus the last speed over time. So the difference in speed divided by the time it took. And now we will make use of it in here, like we made use of speed. We will actually do exactly the same. The difference in acceleration is data dot minus but what is that desired acceleration now? Well, let me also add it here. Actually no, because desired acceleration is not a value we choose. It's a value the flight computer has to choose dependent on the difference in speed. So what we want to do is we want to reduce the acceleration the closer we get to our desired speed. And that will be a simple function. It's practically the same we used for the altitude in episode 3, I think. So define desired acceleration, which depends upon the difference in speed. And in here, we have to differentiate again between positive and negative values, like we did outside of it. Okay, like so. And now, because we do this inside of this function, we don't need it here anymore. This actually will become now dA, because again, we want the throttle be controlled by the difference in altitude, by the difference in acceleration. For testing purposes, let's just wait. Desired. Let's set it to 2. Now, will that work already? Let me think about it. So if the difference in speed is positive, which means we have to accelerate, the desired acceleration will be positive. And if the difference in speed is negative, so we are too fast, we want the acceleration to be negative, so we want to slow down. Okay, that makes sense. Now in here, we do the same we did with difference in speed before, so I think we don't have to change anything in here. Okay, let me give this a spin now. Now this shouldn't change too much. It should just work, but it doesn't. Ah, well, of course. We defined a function and we use it like a variable. So desired acceleration is of course a function. A function is called like that. Now it should work. Nope. Do we use it somewhere else? Desired acceleration, data.desired acceleration. What was the issue again? In line 49, line 32. Ah, of course. We have no return value yet. Return desired. That's it. Try again. Okay, that seems to work. Let's increase the speed. Holy moly, that looks much better than I thought. Not so bad, guys. But of course, it's still not really smooth. Let me land this thing. So now what we need, we have to actually differentiate by the proximity to ds. So the further away we are, the larger the desired acceleration, and the closer we get, the smaller. So if ds is bigger or equal to, let's say, let's start with 10. So if the difference in speed is 10, we want our desired acceleration to be, let's say, 4. Why not? This step now comes down to experimentation. I'll just use some values that feel alright. If it's bigger than 8.0, I think I will fast forward this one. Okay, that shall be enough for now. Now I have to repeat the same on the other side. Only I need negative values. I can do this actually much more elegantly, I think, because again I do the same twice, so I can simply do it once outside of here. And if ds is bigger than 0, I will simply return desired. Otherwise, I will return negative, also minus desired. Delete the rest. I think that should work. Why do I get this problem here? Okay, now. So let me think about it again. I pick a value for my desired acceleration based on the distance to the desired speed. The closer I get, the lower the acceleration. And then I return the acceleration, positive or negative, depending on the difference in speed, whether that's positive or negative. I think it should work. Let's try it again, guys. This already looks quite nice, but the pulsation is still a little too big, I think. But I think we're getting there, guys. Let's check if we can actually go down. Nope, we can't. Okay, I think I cheered too soon. And of course, as I suspected, this was too easy here. Yeah, because the difference in speed can be negative, and we don't handle negative cases at all. I only handle it down here, so what we have to do is to only use the absolute value of the difference in speed. So this function, this built-in function absolute or abs, removes the sign basically. So -1 becomes 1. I think this should do it. That way, when we hit -10 speed, it will still set something. Otherwise, we would default to nothing, because we don't handle cases below 1.5. So let me put an else in here for the minimum desired acceleration, which will be 0.25, why not? Okay, but I need more absolutes here. Guys, I think this should do it. Oh wait, we haven't staged yet. Where's my computer? Here is it. Here it is. Now let's hover. Guys, this doesn't look too bad. But why is our speed negative now? Wait a second. It definitely needs more tweaking, but it works, guys, I think. Let me land and tweak a little bit. That was quite smooth. Okay, so I think these values are a little too big. Guys, I'm just making up these values, so it's a lot of trial and error. Okay, oops, here's an error. Let me try again. I think the throttle increments might be too big. The throttle increments, let me change them a little more slowly. And I think we also need more acceleration in here. 0.5. Okay, like so. Whoa. This looks kinda nice, guys. Now let's hover. Holy moly. Let's go a little bit faster. Yeah, I think we need more acceleration on the upper end, but the low end looks good. Maybe we can change it on the fly. That's maybe a little too much. Oh, now quickly. What do you say, guys? And here we are, guys, back at Soyuz. I want to test now if using the smooth throttle helps against those wobbles. And let's go. Up to 10 meters per second. And hover. Do you see any wobble, guys? I don't. I don't know about you guys, but I find that epic. Okay, guys, so how does that matter in a grand scheme of things? Why do I put all this effort into hovering a rocket? Besides it being incredibly cool, of course. What we've done so far is to make our flight computer able to hold a certain speed. Not any speed, but speed going up. It only cares for that. Now imagine we could do the same but going to the side, if the computer could hold a certain speed going left. And that by tilting the rocket back and forth like it does the throttle. And here comes the point. If we can control our speed going up and to the side, we can get to orbit. We don't have to bother with anything else. Going to orbit seems hard when you think about gravity turns and trajectories, but the essence of that all is just controlling speeds and up and side directions. There is nothing more to it. If it needs to go faster to the side, it would tilt more, and that's a gravity turn. So what we will end up doing is quite simply to change up and side speeds on the fly. First manually and a few videos down the line using a function. Fully automated. Okay, that's it for this video. Auf Wiedersehen and thank you for watching.